There is a second method available for obtaining these isotopes, which was invented 40 years after the first method was discovered. That is, when this reactor was constructed, Californium was produced, and this Californium decayed because its half-life is 2.5 years. But the rest of the isotopes did not decay. They were used as a source of neutrons. When they were depleted, meaning there were no more neutrons in them, they still contained other isotopes of Californium. One can disassemble these old sources, extract Californium from them, and chemically isolate the Californium fraction. In principle, it would be necessary to separate these isotopes again in a separator, and then we would not have Californium-252, but Californium-251, which lives for 980 years. And this isotope can be used since it has only one neutron less than Californium-252. The task is difficult but rewarding, and therefore we decided to carry it out. We took a source out of storage, which was 42 years old. In a similar hot cell to the one that I showed you previously, we cut it open. It turned out that there was another container inside, which was also cut open, taken out, and a fraction of Californium was isolated. This Californium was taken from this old source and applied to a thin foil layer, as I said. And here is this target made of Californium, consisting of 12 segments in which there is almost no Californium-252, amounting to only about 3 micrograms, while Californium-51, 50, and 49 make up the rest. And then this target was irradiated on an accelerator, and we obtained 3 isotopes of element 118 at the same time. Different isotopes, different lifetimes, and different decays. Hopefully in future, it will be possible to separate these isotopes, and then the separated isotopes of Californium could be used at the factory, which would be the next step towards heavier elements. This is what this layer looks like on one segment under an electron microscope. I would like to emphasize that the thickness here is around 0.4 microns, with an approximate uniformity. This is what it looks like, and a beam travels along this layer. The beam has a certain halo, but its highest intensity region is about 3 millimeters, and it is spread to become 9 millimeters wide with a special wobbler, that is, a high-frequency system that has a frequency of about 1 kilohertz. 1,000 vibrations per second spread it vertically, while it is spread horizontally by the movement of the wheel, which moves at a speed of about 12.5 meters per second. Therefore, the beam leaves a trace before moving on to the next one. Then there will be the next, and so forth. Thus it spreads throughout the entire volume. I must say that this is a fairly efficient system. And today, at a maximum beam intensity of 1 microampere of particles per square centimeter, a power of about 0.6 watt is released. That is not a lot. A handshake has the power of about 6 watts, and this is only 1/10 of that energy. However, per 1 square centimeter, 10 square centimeters roughly makes up the energy of a handshake.